Howdy and welcome back. We'll begin with a motivating example here for our introduction to class lesson. So motivating example, let's assume that we're reading in RGB values from a formatted file. Let's assume that it's just going to be simply a number of integer values, and each triplet will be considered those of the red, green, and blue component for a color. At this point in the semester, we probably can determine one of two ways of doing this. The first might be that as we're reading from the files, we're going to have three parallel vectors. One will store all of the red values we observe, one will store all of the green values we observe, and one will store all of the blue values observed. What we mean by parallel vectors is that, say, the first color we read, we would go ahead and assign its R component to R values at 0, its green value to G values at 0, and its blue value to B value dot at 0. We say that these three vectors are in parallel because for a respective color, essentially at the 0 index of each of those vectors contains the relevant integer value uh, for the specific component of color that we're looking for. So we go ahead and we open up our file. We go ahead and ensure that it's opening before we move on. We declare these three vectors and we begin reading triplets from our input file stream. And again, the R component is pushed back to R values, G to G values, B to B values. And at the end of this, we can think about having, say, three vectors, each of one element. And then the second time we go through that, we can see these vectors being expanded by one to carry on the second. In a respective color, whether it's, say, the first one we read, each of the RGB components would be at position 0 across these three vectors. And then the second read, the corresponding triplet of values would be pushed across the first index of these three values. And then if we're looking at, say, the first color that we've read in, we would go ahead and look into our values at position 0 for each of these. An alternative way might be to go ahead and create a two-dimensional vector. This gets a little confusing because we're not actually labeling the slots with where these colors are residing. For instance, let's go ahead, same process. We're reading a triplet of integer values from a file, and using the two-dimensional vector colors, what we could do is simply push back a vector of those RGB values to that two-dimensional vector of colors. So in this case, we would begin. The first read would essentially have our vector having one element at the 0th index, which would be a triplet of values. The second read would push back an additional vector, and we can see here that a multiple two-dimensional vector is indeed forming. We could then access the various color components by writing something like colors dot at 0 to get the first color that we read. And then if we wanted its R component, we could write something like dot at 0, assuming that the R component occupies the 0th index of that two-dimensional color. If we wanted the G component, it would be the same, but at index 1. And then if we wanted the B component, it would be at index 2. However, if you look at this, you notice that it's not quite clear what's living at each index. It would be a lot nicer if we could do something where essentially we could have these fields labeled. For instance, you might think, okay, I'll use a struct, call it color, and say int RGB, and then I could do something like color C, and say c dot r's equal to some value, and then have a vector of colors. This is the direction we're going, but we're going to see here that we can do something a bit more powerful than this to ensure that, say, whatever object we're using to represent our colors is always going to store valid color values. So what we will see is the direction is going to be towards types. Types are good for representing ideas in our code. They're helpful because they're going to provide both a representation. For instance, in the struct example, there were 3 different fields that we needed to store in our integer value G, integer value B, integer value. Well, we can go ahead and represent that in our structure. What's going to be new today is when we bring into this idea of classes, we're going to begin defining various behaviors or things that objects of our user-defined types can do. We'll get into what that means and the implications thereof. But one of the powerful things that we will be introducing is an idea that through invariants, we can construct objects that will always follow, in this case, say what it means to be a valid color. And we can have checks to ensure that we never essentially deviate from that. So the concept of a color is going to follow our pattern of a type. A specific color is going to be represented by 3 integer values, which will come to be known as the data members of our type. We will then introduce how it should be possible to also perform various operations on colors. And the result of, say, those operations would be dependent on the underlying state of the object to which it's applied. Therefore, we would like to represent an abstraction of our notion of color as a data structure along with a set of functions that can perform these sorts of color operations. The class language construct in the C++ programming language will yield an ability to introduce user-defined types into our program. We will leverage this construct to write a user-defined type color towards the end of this lecture.